AI agents are essentially computer programs that can act on their own to achieve specific goals. They do this by perceiving their environment, collecting data, and using that data to make decisions. AI agents can range from simple programs that follow a set of rules to complex systems that can learn and adapt over time. Here's a breakdown of how AI agents typically work. Perceive the environment. AI agents use sensors to gather information about their surroundings. This could include things like cameras, microphones, or even just data feeds from other computer systems. For example, a self-driving car uses cameras and radar to perceive its surroundings, including other vehicles, pedestrians, and traffic signals. Process information. Once they have data, AI agents use algorithms or machine learning models to process it and make sense of it. In the self-driving car example, the car's AI agent would use machine learning models to identify the objects it sees in its cameras, as well as to track their movement and predict their future behavior. Take action. Based on their understanding of the environment, AI agents can then take actions to achieve their goals. This could involve anything from sending a text message to controlling a robot. The self-driving car's AI agent would take actions such as steering the car, accelerating, or braking in order to navigate safely and reach its destination. Learn and adapt. Some AI agents are able to learn and adapt over time. They can do this by storing information about their past experiences and using that information to make better decisions in the future. For example, a virtual assistant that is used to book appointments might learn over time about the user's preferences and schedule, and use that information to suggest more relevant appointment times in the future. AI agents have a wide range of applications, from helping us with our daily tasks, like virtual assistants, to controlling complex machinery, like self-driving cars. As AI technology continues to develop, we can expect to see even more innovative and powerful AI agents emerge in the future. Here are some specific examples of how AI agents are being used today. Customer service. AI agents are being used to provide customer service by answering questions, resolving problems, and even making recommendations. Manufacturing. AI agents are being used to automate tasks in factories, such as quality control and assembly line operations. Healthcare. AI agents are being used to analyze medical data, diagnose diseases, and even develop treatment plans. Finance. AI agents are being used to detect fraud, manage risk, and provide investment advice. There are several main categories of agent architectures, each with its own strengths and weaknesses. Reactive architectures. These are the simplest type of agent architecture. They function by directly reacting to percepts, sensory inputs, from the environment without maintaining any internal model of the world. A classic example is a thermostat that simply turns on the heater when the temperature dips below a certain point and turns it off again when the temperature rises above another set point. Reactive agents are efficient and fast for simple tasks in controlled environments. However, they struggle to handle complex situations that require planning or adaptation. Imagine a reactive agent controlling a robotic vacuum cleaner. If it encounters an obstacle, it might simply bump into it repeatedly until it accidentally finds a way around. A more sophisticated architecture would be needed for the robot to navigate its environment effectively. Deliberative reasoning architectures. These agents are more complex and powerful than reactive agents. They have an internal model of the environment, which they constantly update based on new percepts. This model allows them to reason about the world and consider the potential consequences of different actions before taking one. This is essential for tasks that require planning, such as playing chess or navigating a maze. Deliberative agents can also learn and improve their performance over time by refining their internal models and decision-making algorithms. However, they can be computationally expensive, especially for very complex environments or tasks with many possible options. For instance, a deliberative agent controlling a self-driving car would need to consider not only the position of other vehicles and pedestrians, but also traffic laws, weather conditions, and the possible actions of other drivers. This can be a lot of information to process in real time, and it can be challenging to develop algorithms that can efficiently evaluate all of the options and choose the best one. Layered/hybrid architectures. These architectures combine elements of both reactive and deliberative architectures. They typically have multiple layers, with lower levels handling low-level, fast response tasks based on predefined rules or behaviors. These lower levels can handle situations that require immediate responses, such as a self-driving car needing to slam on the brakes to avoid a collision. Higher levels in the hybrid architecture focus on reasoning, planning, and decision-making. They use the information gathered by the lower levels to make more complex decisions, such as planning a route, navigating traffic, and adapting to unexpected situations. This layered approach allows hybrid agents to be both fast and flexible. They can react quickly to urgent situations while also considering long-term goals and planning their actions accordingly. Self-driving cars are a great example of a hybrid architecture in action. Their lower levels might be responsible for basic tasks like steering, acceleration, and obstacle detection using pre-programmed responses. These lower levels would allow the car to react swiftly to avoid imminent dangers. Higher levels would handle more complex tasks such as route planning, traffic law interpretation, and decision-making about lane changes or overtaking maneuvers. This layered approach allows self-driving cars to operate safely and efficiently in dynamic and unpredictable environments. Here's a table summarizing the key differences. Architecture. Description. Strengths. Weaknesses. Reactive. Respond directly to percepts. Fast, efficient for simple tasks. Limited ability to handle complex situations or plan ahead. Deliberative reasoning. Use reasoning and internal models to decide on actions. Powerful for complex decision-making. Slow, computationally expensive. Layered/hybrid. Combine elements of reactive and deliberative. Fast, flexible. Can be complex to design and implement. Export to sheets. These are just the main categories, and there are many variations and subtypes of agent architectures within each category. The best architecture for an agent will depend on the specific task it needs to perform and the environment it operates in.